Hello, this is module 4, investigation 4. So we're looking for the partial and unit growth factor. So number one, express your understanding for the exponents by answering the following questions. So A, in the term b to the x power, what does the x represent? So the x is in here is gonna be the input value. So x is the x is input value. And then what does the b to the fifth power represent? And this time it's gonna be, so b to the fifth power means, actually you should understand this, it's gonna be b times b times b times b times b, which is, it's a product where b is a factor which has been multiplying for 5 times. So evaluate the 4q, which is 4q means 4 times 4 times 4, which is it's a 64. Now calculate the following. So now instead of the nice integer as a power, you got the 9 to the half power, which means in order to get the 9 and go to the 9 square, which is 81, it's been multiplied by 9, right? But you just need to go to half of from the 90 to 91, which is you need to put it as hold on a second. I shouldn't say this way. Okay, let me take out it this way. So it's 9 to the 0 power, which is 1, and then 9 to the first power, which is 9. So, but we are looking for the 9.5. It's in between, right? It's in between. So what you do is, okay, so as a first power, you need to put the actually half of the 9, which is a 9 is actually the 3 square, and half power, as a power rule, you can cancel, so it is a 3. So this is same as actually the square root of 4, which is makes a 2, and then it makes a square root of 121, which is 11. So what do you answer in B represent? In general, how do you about determine the value of the sum number B raised to the half power? So because of half power, I can say that the quantity growing exponentially because of power, but half unit interval. Okay, so that's how they represent the half unit here. All right, so D, in general, how do you know about the determine the value of the x to the 1/3? So same thing, the quantity also growing as a power, but this time is a 1/3 unit. So if you want to calculate the 4 to the 3/2 power, which is as a 1. What does the answer represent? So it's going to be the quantity growing exponentially, but this time is 1.5 unit interval. So instead of the 1 and 2 and 3, it goes with a 1.5 and then 3 and 4.5 like that. Which is, if you want to calculate that, so 4 to the 1.5, which is 4 to the 1.5 power, which is 8. All right, solve the following the equation for x this time. But is it different from the actually the square and the square root? Okay, so we are looking for the value of the here. So as you notice, 9 makes 81. Also negative 9 also makes 81. So this x is actually the plus minus 9. X cubed, but only the 20 become 27 is actually the 3 is. Okay, so this x equal to 3. But this time, actually, we have to think about carefully. So we need to put that as this time What's a good way to do it? So another way to solve this one is you need to get rid of the 3 over 4, which is if you put the fourth power on both sides, right? And that means you got x by itself as a first power, and then the 8 to the fourth power is going to be a 16. And same here too. If you put the power 5, and then x cancels, and then you got 32. Now, we wanna actually the review for the exponent rules. So when you multiply two numbers with the same base, you can just add up the exponents, which becomes 8 to the 6.5. And then when you have a division as a quotient, you can subtract the exponents, which is b to the 5.8 power. And then when you have a power over 2 power, you multiply, which is we call the power rule. So c to the 6.2. All right, number 2. You are given as 4 and 38 and 7 and 50 are two order pairs for the exponent growth function. Your classmates notice that the difference in output is 12 as the input changed by 3. Create the table showing some additional order pair. So explain how you know that the two additional order pair, bolded, cannot be accurate even though we don't have a function, formula, or graph for these functions, because we need to try to make that as the exponential growth functions, which means not linear. So x is actually the increasing by 1 as an addition, right? So in order to get that, so you have to think about how much is actually to think about it. So if you want to find the ratio, right? Ratio, which is I want to say R, it should be the 50 over 38, which is 50 over 38 is about 1.32. Okay. So in order to get that number, but this is actually the 3 unit growth factor. Okay, it's a 3 units because it's from the 4 to 7 as a jump, right? So the R was 1.32 as a 3 unit. So in order to make this whole thing as a 1 unit growth factor, we need to put the 1/3 power with it. So 1.32 to the 1/3 power should be equal to the 1.10. So in order to get a next number, instead of the 42, what I needed is increasing. I need to 38 times by 1.1, which is this one should be the 41.8. And also 41.8, I need to multiply by 1.1. I got 45.98. And then 45.98 times by 1.1, I get the close to 50. Okay. So, yeah, so in order to make the exponential function, we have to use the factors. Okay. And then, yeah, I think that's all we need to do. Okay. Alrighty. Okay. So next page. So now number 3, urban planner noticed that the population of the certain county doubles over 20 years from 1990 to the 2010. Following a pattern of the exponential growth, the population of the county was 756,000 people at the end of the 1990. What was the population of the county at the end of the 2010? So we are actually checking for that problem from the the 1990 to the 2010, right? So population counting of the at the end of 2010 was 756,000, and it makes a double. So I got 1,512,000 people. So if the growth pattern were to continue for another 20 years, which is 2030, what will be the population? So what do you do is same thing. Starting from the 1,512, 1,512,000, and then multiply by another 2, and then it makes 3,024,000. So which means this is the same as 756,000, and then multiply by 2 squared. Because you multiply by 2, because it makes the doubles every 2 years, 20 years. So which quantity are changing in this situation? So changing quantity is time elapse, which is from the 1990, and then also the population of the county is changing, right? So the changing is the time elapsed from 1990, and also the population. Of the county. And also what is not changing, which is the initial value, which is the initial people, and then the growth factor, which is double, which is 2 times. So if we assume that this population growth will continue into the far future, complete the table. So 0 year was 756,000, and 20 years later, double of the 756,000, so 1,512,000. And then another 20 years, double of the 1,512, so 3,024,000. And then double of that is 6048000, and the double of that is 12,096,000. So current population of the how many times? As large as is 2 times, because this is 2 to the 0 as an initial, the now multiply by 2, multiply by 2 square, multiply by 2 cube from the initial, and then to the 4, and then population n, which will be the initial from the 756,000, and then doubles to the nth power for 20. But n increased by 20 though. So n is 20-year growth factor. Okay, so number 4. Since the 20 change in time are quite long, so we might want to know how much the population changed short periods of time. So given the population grew exponentially, which statement 1 and 2 are best to describe what happened every 10 years? Instead of the 20 years, I want to make the every 10 years. So number 1, every 10 year population growth by the constant amount. That is, the constant amount is added to the population at the end of the 1990 to get the population at the end of 2000. And the same amount is added to get the population at the end of 2010. Second, every 10 years population increased by the constant factor. So this is a different amount, right? Factor. And that is a constant factor is a multiply the population at the end of 1990 to get the population at the end of the 2000. And then this constant factor is multiplied by the population at the end of the 2000 to get the population at the end of 2010. So this must be a number 2, right? Because this is exponential growth. So given that the population increases exponentially and double over 20, what is a 10-year growth factor? So which is, it was 2 to the n was So 20-year growth factor, so 20-year. Now we try to make a 10-year, which is half of it. So you can just meet the half of the time period, okay? And then what about 1 year? So it was a 20-year as, but you need to try to make the 1-year growth factor, which means there are 20 of the 1 year, right? So n divided by 20. So you can plot this way to get the answers out here. Which means instead of the 2, n, actually you can just ignore this one. So n and n. So you can just make the 1/2. And then instead of the n, because we're just talking about just the factors, growth factors. So I can say it is 1/20. So 2 to the 1/2 power is about 1.414. And this is going to be the 1.03526, okay? All right, next page, please. So number 3, what is the 2-year growth factor now? And then what is the 3-year growth factor? So now what I do is 2 to the, so 2-year growth factor, think about how many, how much is 2 years in 20? I think is the 10, so right? So I want to say 1/10, which is 1.07177. And then 3 years. So how many 3 years in 20? So I want to say it's hard to divide it, so you can just say 3/20, right? And then becomes 1.10957. How about 7 years? There are 7 out of 20, and then you get the 1.27456. So complete the table. So 0 year was 756,000. Now the first year, so what you need to do is because of 1 year later, right? So first year, I'm using the, so I want to define the formula to get this out, okay? So as the population of the county, so T is 756,000. And then I want to make that as T over 24, the every year. Okay, so now you can plug it in 1, and then I get, if you plug it in this 1 to here, and then 2 here, and 3 here, 13 here, and 16 here, and then 20 here. So you can just get this amount, okay? So 782, 660, and 810,261, 838,835, 1,186,291, and 13,162,007. 1,316,272, and then 1,512,000. Okay, so you can find anything from here. Now, define the function h that represent the population county C month since the end of the 1990. Okay, so now what we need is the h function. We try to get that out as the month. So T is about the year. So now how many months a year? So we have to do it as 2 of. So instead of the T, we need to put out as a month. So from the 1/20 as a year, every year. And then that is actually the 12 month. And then we put down as a T. Right? So which is 756,000. Okay, let's put that as a C as a month. Okay, that's what they say here. Sorry about that. So let's change to the C. Change it as a C here. C over 20. And then you got 2 to the C over 240. So there are 240 months in 20 years. Okay, so I think that's all. And then number 5, a farm in Canada, which is this problem will come back later. So I want you to actually understand. Okay, So a farm in Canada has 218 alpacas on January 1st, 2004. After 8 years, alpaca population decreases to 187. And assume the number of the alpacas decay exponentially. So the number of the alpacas decreasing. What is the 8-year growth or decay factor? So this time is a decay factor. Okay, so how do you find out? You need to just divide the two number of the alpacas. Okay, so 187 and divide by 218, which becomes 0.858. And then B, fill in the blank. The number of the alpaca on the farm on the January 1st, how many percent is that? The change to the percent. So you got 85.8%. Okay, that remains. So what is 8-year percent change, which is 85.8, subtract the 100%, which is negative 14.2% decrease. So D, assume the alpaca population continue to model the same exponential model. How many alpacas can expected in the 2020? So 2020 is how many years later than the 2004, which is 16 years. So if you use that, the 0.858, which is that's actually the 2020 from the 16 years. Okay, so but it's decreasing by the every 8 years. So 16 is twice of 8. So you can just put that as a square with the number of the alpaca, which is about 218. And then I'll get the 160 alpacas at the time. So now E, since the 8-year change in time are quite long, so we might want to know how the population of alpaca change over a short time period. What is a 1-year growth factor? So 0.85A was every 8 year. So I want to change to the every year. So I want to say 1/8. Okay, and then I'll get that as about the 0.981. All right, so yep, that's all. And then what is a 1-year percent change? Now you gotta change to the 98.1%. So 98.1 subtract 100, negative 1.9% decrease every year. And then define the functions as now I want to say 1 year this time. Okay, so initial value was 218 on 0.981 and 1 t over x over 8. Sorry, x over 8 or t over 8, whatever. Okay. All right, so then you can figure out the number of the alpacas in any years. Okay, 6. Assume the number of the alpaca continue to change by same decay factor each year as defined as exercise 5. Use the calculator to determine the following cell. After how many years will be there is a 109 alpaca. So now 109 with a 218 of 0.981 to the t, and then you're solving for t, which is about 36 years. Okay. And then after how many total years will be the 50 alpaca? So 55 now from the 218. Oh, sorry about that. 218, 0.981 to the t power. Okay, or t over a, whatever, yeah. And then you get the t is going to be about 71.8 years. Okay, so you can change that as f of t is 218 of 0.981 to the t power. So it changes every year. All right. Now after how many years the 120 alpaca decreased to 60 alpacas. Okay, so now it was now decreased to 60 from the 120. From the ratio is 0.981 to the t power, and so for t is about 36 years. Okay, so that's all for the change in the growth factor. Could be any of the time period. Thank you for listening.